So we've seen that based on the values of f at different distances from the center, we conclude that estimated result somewhat less than 3. The interpretation is fairly straightforward if we consider this to be a thin sheet of material that's denser here than it is here. For example, this end might be steel, this end might be glass, and there might be different proportions of steel and glass between here and here, and I'm not sure it's even possible to combine steel and glass with their different melting points and so forth, and the density differences. That would probably take a little bit of doing. But in any case, you imagine that something is made of a dense material here and a significantly less dense material out here, and you're estimating the mass of this entire wedge. Another interpretation could simply be in terms of volume. If we come into 3 dimensions here, divide the axes by units, our region would be this, and let's go ahead and sketch dotted lines along the r equals 1 and r equals 2 contours, as well as the solid line along the r equals 3 contour. When r equals 0, the value of our function is 1, so let's just say that this is 1 on the z-axis, kind of exaggerating the z-scale compared to the x and y scales. When we get out to the r equals 1 circle, as we've seen, the value is 1/2, so we can sketch the arc at the value z equals 1/2. When we get out to z equals 2, r equals 2, our value is 1/3. We can make a sketch of that contour line, and by the time we get out to r equals 3, the value is 1/4. We'll be here, and I'm not explaining how I'm constructing this sketch, but it should be fairly obvious. Okay, now if we draw our contour in the YZ plane and our contour in the XZ plane, and finish shading, we get a reasonable picture of a solid figure. And our interpretation in this case is that the integral represents the volume of this portion of a figure, of this portion of a surface. With this picture, we could make another estimate. Remember, the area of our base here is 9 pi over 4. The altitude here is 1. The altitude here is 1/4. On the average, how high is this surface above its base? Certainly between 1/4 and 1, probably closer to 1/4 than to 1. And in fact, because of this picture, I would say it's probably average altitude of this thing is probably around 1/3. And 1/3 of 9 pi over 4 is about equal to 2.3. With our former estimate 3, I can then say I kind of expect this integral to come out somewhere between 2 and 3. Maybe it's greater than 2. Certainly it should be less than 3. Well, it's time for the payoff. Let's do the integral and see what we get. First of all, let's just consider the integral antiderivative of 1 over 1 plus r times r, so that put the r in the numerator here. The integral of r over 1 plus r dr. This is fairly easy to integrate, and if you've been doing some integration, this is a pretty common trick. We're going to let u equal 1 plus r, so that r equals u minus 1, du equals dr, so this integral becomes the integral of u minus 1 over u du, which is the integral of 1 minus 1 over u du, which is u minus the natural log of the absolute value of u. Now, substituting back 1 plus r, we see that our integral of r over 1 plus r dr is 1 plus r minus the natural log of the absolute value of 1 plus r. It follows then that our integral from 0 to 3 of r over 1 plus r dr equals the change in this quantity, and that's going to be 1 plus 3 minus the natural log of the absolute value of 1 plus 3 minus 1 plus 0 minus the natural log of the absolute value of 1 plus 0. 1 and 3 is 4, minus 1 is 3. Natural log of 1 plus 3 is 4. Natural log of 4. Natural log of 1 plus 0 is a natural log of 1, which is 0. So what we get here is going to be 3 minus the natural log of the absolute value of 4. Now E is about 2.7, 2.71828, etc. About 2.7. If we square 2.7, we get about 7.3. 4 lies between 2.7 and 2.7 squared, so this natural log will be somewhere between 1 and 2. So we're going to be subtracting a number between 1 and 2 from 3, giving us a number a little bit less than 2. So I'm going to just estimate that in my head. Maybe 1.5. Okay, the natural log of 4. 4 is pretty close to geometric mean between 2.7 and 7.3, the square of the 2.7. So now what is our integral? What's our complete integral of our function here? It's the integral from 0 to pi over 2 of the integral from 0 to 3 of 1 over 1 plus r times r dr d theta. The integral, the r integral, is just 3 minus the natural log of the absolute value of 4. We're integrating with respect to theta. Well, the integral of a constant with respect to theta is just the constant times the integral with respect to theta. The integral with respect to theta, well, antiderivative of just d theta is theta. So that what we end up with here, and I'm kind of having to squeeze it in, but let's see. The integral from 0 to pi over 2 of d theta is just pi over 2. So what we get is pi over 2 times 3 minus the natural log of 4. Let's bring that back over here and say then that this integral, if I've done everything correctly, should be pi over 2 times the natural times Going to have to fix that. I'm not going to bother to repair it. I'm just going to put a redundant set of parentheses in here. Times 3 minus the natural log of 4. Okay, so that's pi over 2 times 1.5, question mark. Pi over 2 times 1.5 is going to be about 3 times 1.5, 4.5 divided by 2. I'm estimating about 2.3. Okay, my estimate of the natural log of 4 was probably a little bit off. The actual here is 2.53, and I believe that's rounded correctly to 3 significant figures. So in any case, our result is clearly in keeping with the estimates that we made based on the picture of the volume region and on the values of our function at different contours. This would be the mass of the region having this density. It would be the volume of the figure that we've sketched here. Accurate to 3 significant figures.